Hi there, I'm Cypher with another video and welcome to our platform Data Science Era. As you can see, the topic of this class is linear regression analysis using SPSS. If you think that this knowledge is really helping you, you can subscribe my YouTube channel and you can also join our Facebook page, Facebook group, and our website will be launched soon, www.datascienceera.com. Alright, so let's begin this class. The topic I will discuss in this class is at first, I will show you simple linear regression, like how to check all the assumptions, how to fit the model. Then I will show you for multiple linear regression, how can you check the assumptions and interpret all the things in a model. Alright, and as you know that before starting this class, and in fact every class, you need to download the data file I have provided you. Especially for this class, I have provided you 2 data sets. You can check this in the description box if you're watching this video from my YouTube channel. Okay, so when you can fit simple linear regression model, you have to remember that to fit a model, simple linear regression model, should be a one independent variable and one dependent variable. All right, like for the dependent variable, the variable type has to be continuous. I showed you for quantitative variable, there are specifically 2 particular types, discrete and continuous. I hope you remember that. And for the independent variable, it also has to be continuous. Okay, and moving forward, for multiple linear regression model, there has to be one dependent variable, and for the independent variable, there can be more than one independent variables. Okay, and for the dependent variable like simple linear, it has to be continuous variable. But for independent variable, it can be continuous variable, it can be categorical variable. All right, and the goal to fit linear regression model is you can predict new values for the dependent variable given the independent variables. Also, you can explain how much variation in the dependent variable by fitting a regression or by showing a regression equation. All right, and moving forward, assumptions of linear regression model. This is very important. A lot of people I saw that they just fit the model without checking assumptions. You have to check all the assumptions, whether it fulfilled or not. You have to check whether there is a linear relationship between dependent and independent variables or not. Then there should be no autocorrelation, or the observation need to be independent, and there should be no significant outliers, and there should be no heteroscedasticity. And residual errors need to follow approximately normal distribution. Also, there should be no multicollinearity. If you do not understand all these terms, I request you to check my basic videos, which I have not uploaded yet. I will try to upload some basic videos for that. Even in fact, in this video, I will try to explain some of the terms a little bit. Okay, so now let's move forward with SPSS. Okay, so here for the first data set, there is only 2 variables. Okay, as you can see, there are one variable which is actual weight. And here weight means for a particular car weight. Okay, and this is for car miles per gallon consumed. You can also mention it in the level to understand it more specifically. All right, so here it is, cars weight. And now think that which one is dependent and which one is independent. As we all know that, car's weight can be independent here because car's miles per gallon consumed, it has to be dependent variable because it depends on car's weight. If there is more weight, usually there is a high chance that you will consume more gallon. All right. So now as you can see, there are 2 variables to fit the simple linear regression model. You cannot fit here multiple linear regression model. Why? There is only 2 variables, one dependent, one independent, and both of them are continuous. You can also see this in the measure of the variable, both of the variable are scale. That means they are quantitative variable. I hope you remember that. And now move forward to fit in the model. You have to check all the assumptions as I said. Firstly, let's try to check the linearity. Okay, the linear assumptions. What you need to do, you can go to the graphs and go to the chart builder. Then you can click here the scatter or dot. Okay, you have to draw a scatter diagram. So for simple, you can just click here and drag it here. And for the x-axis, you can select the independent variable, which is, as I said, the car's weight. And for the y, you can check the car's miles per gallon consumed. So now then you can click OK to get the output. Alright, so let's open the output. So here you can see for the scatter diagram, there is almost linear. How you can check the linear? As you can see here, it's almost like a straight line. Alright, if it is not a straight line, then that is not linear really. You can just make a double click and click here. And as you can see, there is a fitted line here. That is our goal, in fact, to do this regression analysis, to find the fitted line or find the regression equation for this fitted line. As you can see, the fitted line is almost linear. Okay, so all this value is very close to this fitted line. So you can say that this linear assumption fulfilled. Now we have to move forward for other assumptions. Well, you can check other assumptions by in fact feeding the model. So now you can directly feed the model. To feed the model, you need to go to the analyze, then go to the regression, then go to the linear. Okay, now as I already selected this before, so let's click reset. Now select car's weight in independent and car's miles per gallon consumed. You can select it in dependent. Alright, now our variable are selected. Now you can click statistics, you can estimate, you can also check confidence interval, then you can click R-squared chance. It is not something which is very important. Then you can also click descriptives. You can check mean, median. For this you need to avoid, you can avoid collinearity here. I will describe that a little bit later. You can click Darwin-Watson, you can click case of diagnostic, and then you can click continue. Okay, then you can click plots, and you can click Z predict here in X variable in Y and Z residual in X. Okay, then you can also check histogram and normal probability plot. Then click continue, click OK. Okay, now I will explain that why I'm clicking all those particular things. Let me open an interpretation files too, so that I can also show you that how can you interpret this output. So here you can see our output files here, and I also open an interpretation files. Now let us check the second assumptions like autocorrelation. Before checking that, here you can see in the output there is a descriptive statistics and correlations. So what is correlations? Correlations actually tells you the linear association between two variables. For example, here you can see that the correlation value is minus 0.7. Well, it actually tells you that, if the value is 0 to 1, and there is a positive correlation. Okay, if the value is 0 to minus 1, there is a negative correlation, especially if it is greater than 0.66, there is a strong correlation. Now you can see for the negative correlation, there is a strong negative correlation here. That means if car's weight increases, then car's miles per gallon consumed decreases. Okay, so here you can see here for the next table like model summary, here you can see there is a value Darwin-Watson. You can also use this value to check the autocorrelation. Okay, now to check the autocorrelation here, like how we can interpret this, you can say that if Darwin-Watson statistics is close to 2, then you can say that there is no autocorrelation. So here you can see it is 1.9, almost close to 2. So this assumption also fulfilled. Now let's check one more assumptions here, like detecting outliers. For to check outlier, you need to check this particular table. Here you can see the standard residuals. If this value is between -3 and +3, there you can see in the interpretation files I have explained this, then you can see that there is no significant outliers in this data. So this assumption also fulfilled. Here you can see because this value is like for the minimum there is 1 point something, -1 point something. For the maximum there is like 2 point something. So yeah, you can go with the next assumptions. For the next assumptions, you can check the normality assumptions. Here you can use the histogram for the dependent variables, and it actually for the residuals values. Okay, so and you can also check the PP plot. Okay, now here you can see if this is straight line, if all the values or all the values are close to this straight line, then you can see that okay, it fulfills the normality assumptions. Okay, and also you can check it in the histogram, it is also fulfilled the normality. So you can use both these diagram to explain there is normality assumptions or not. Okay, now before going to the next assumptions, like what is autocorrelation that I described a little bit before? Well, autocorrelation is actually showing you that whether the observation is independent or not. Like, like if you ask me a questions, I'm giving you a particular answer. And if you ask me the same questions from another respondent, if he is influenced by my answer, then that is not a good way, right? Like it is not independent. So what I am answering and what he's answering should be independent. Okay, so that is how one kind of autocorrelation. There is also some other way to describe it. As I said, this video is all only for describing the interpretation, and you must know outlier and normality, I hope so. And the one more assumption is like heteroscedasticity. Well, heteroscedasticity, you can find it just as you can see here, all the values is between -3 and +3. And there, if it follows a particular pattern like this or like this, then you can say that there is heteroscedasticity in the data. Okay, then if there is a heteroscedasticity, or there is a, like as I said before, normality, if all these assumptions violate, it is not feasible to fit a linear model. Sometimes you can use some transformation or some other methods to remove this error that we are having, but it's not feasible options for all times. Okay, let's describe that a little bit later. So here you can see that all the assumptions are fulfilled. Now we can go with our model. Okay, now to describe the model, you need to check the ANOVA table and the model summary table. Okay, at first, then you can check the coefficients table. From the ANOVA table and model summary table, you can see that the p-value is less than 0.05. We consider 0.05 for 5% level of significance. We consider 0.001 for 1% level of significance. As you can see that this, here you can set the null and alternative like this way. All right. Now you can see that the null hypothesis is rejected. So you can see that this model is a good fittings. Okay, that means the model is significant. Now this, if the model is significant, then we can go with our next term. But before that, you can also describe like how good the model is fittings by using the R-squared value. As you can see, the R-squared value is 0.492. You can multiply it in 100 and you can convert it into percentage, that you are having 49.2% of the total variation of the dependent variable can be explained by this regression model. Okay, this is not something which is highly, like this is not a high amount of value, like 49%. If it is like close to 70 or 80%, we can say that okay, that is like a big amount. Okay, so why this value is a little bit lower? Maybe there are a lot of other variables which is influenced, or which is which is actually influenced by our dependent variable MPG. That means MPG not only depends on car's weight, it may depend on many other things. Okay, so I hope you understand that. And now the coefficients, which is the most important thing for interpreting a model. And for the coefficients, you can see that here in this table, also in this interpretation tables, like there is two values, constant and weight. And both of the p-value is less than 0.01. So it is significant at 1% level of significance. Okay, so now you can interpret this. You can interpret this in this way, is that as beta here 0.003. So you can say that the expected miles per gallon consumed decreases. Why this decreases? Because there is a negative sign. So the expected value of, like for dependent variable, decreases for 0.003 units for increasing 1 unit of car's weight. That is what you can say from a particular model. That is how you can make a prediction. Okay, and there is also value. This is very interesting. This is called like alpha constant or whatever, or that value is like 32. Okay, this is regression coefficients like for beta, and for alpha we say that this value is like intercept in a model. Okay, now how can you describe the intercept? Like you can say that the expected value of miles per gallon consumed is, well, okay, that means the dependent variable, the value of the dependent variable is this amount of units when there is no car's weight. That means when the value of car's weight is 0. Okay, so this is also another one to interpret in the model. Now, what is our regression equation? A regression equation, how you can describe it, like y is equal to alpha plus beta x. Y is dependent, x is independent. Okay, so you can say CT-ampage is equal to alpha. Here you can see the constant value 32 minus plus minus, so that multiply you get minus 0.003, that means the value of beta, and into x. Here x is car's weight. So this is here our regression equations. Okay, that means this is our final findings of this model. Now if someone is saying you that, okay, when the car's weight is 3,000 pounds, what is the amount of miles per gallon consumed of a particular car, then you can just use this value in this regression equation. Also you can have alpha beta, then you can find that how much how many units the miles per gallon consumed for this particular value. That is the power of fitting a regression model. So here I showed you a simple linear regression model. I will also show you another one where you can actually, where you have to use a transformation. Then I will describe a multiple linear regression model. Okay, so here is the second data files that I have provided you. Here, as you can see here, there is 6 variables here. Here is only one categorical variable and the rest of the variables are quantitative. Okay, now, like as you can see, there is GDP, like mean years schooling, and child mortality, life expectancy, adult literacy, tons of carbon dioxide. So here actually our dependent variable is life expectancy. Okay, and life expectancy for different countries here in the data. Okay, now we have to check that which variable life expectancy depends, like it may depends on a country's GDP, which is gross domestic product. Okay, and it may also depends like mean years schooling of a country's people. Okay, so here let us try to fit the model. So let us try to fit a simple linear regression model at first. Let's say we are trying to fit with the life expectancy and GDP. Okay, life expectancy is dependent and GDP is independent. Okay, so at first we have to check, I hope you remember, you have to check a scatter diagram and to check the linearity assumptions. So here you can see it is already selected. So let me reset this. And select the scatter dot and this, and let me choose gross domestic product in probably in x-axis, right, as it is independent. And for the y-axis we can choose the dependent, it is life expectancy. And now click OK and check the graph. As you can see, this graph is non-linear because you cannot determine it all the points in a straight line. Okay, so now you have to convert it in linearity. Now this is one interesting thing that I'm going to show you, that how can you use a transformation to convert it into linear. It actually not always feasible options, like there are some cases maybe you will not get linearity because of too much non-linearity. So let's try to do this. So what I will try to do is that I will try to click transform and then compute variable, and it is already given here. So let me reset this. Like you have to select GDP. Okay, I'm sorry, you just need to write it down here. Say log GDP, just write down the new variable. Okay, so the existing variable is GDP and you have to convert it into log GDP. Just click LG10, that means 10, and bracket, then use the variable name GDP. Okay, GDP, and now it's done. Now just click OK, and there will be a new variable which is named as log GDP. As you can see here, the new variable created. Now you can see there is also a data view, like new data created for these variables. And what I'm trying to do is that I'm trying to create the graph again. Okay, so to create the graph, you just need to go to the graphs options, then click chart builder again, click OK again, and now you can click reset again, click scatter dot, and then x-axis. Now you need to choose log GDP, not GDP. Okay, so if you choose log GDP here, and then you can choose like life expectancy at y-axis, then click OK to get the graph. Now you can see there's interesting things. Now you can see that it looks linear. All the values are very close to the straight line. Okay, all the points in fact. So I hope now you got it. Now you can feed a model and go to the and check all the assumptions. Okay, I'm not gonna show it again like feeding a linear model, simple linear model. Now let me choose like a lot of variables. Okay, let me try to feed a multiple linear regression model. So go to the analyze, go to the regression, and then go to the linear. And here I already choose some variables. You can click reset, and for the y axis, like for dependent you can choose life expectancy, for independent you can choose GDP. No, you cannot choose GDP because we already checked linearity for this variable, so you have to choose log GDP. Well, I haven't checked the linearity with all these variables, okay, but I am choosing this variable. So what do you need to do? You need to check the linearity with life expectancy, okay, by drawing a scatter diagram that I already showed 2 times. Okay, then go to the statistics. So here in the independent we are selecting more than one variable, so this is multiple. Okay, now click statistics. You can click Darwin-Watson case was diagnostic. Now you can click collinearity diagnostics. Well, the reason why we're choosing collinearity diagnostic, I'll describe this a little bit later. Click plus, and as usual click Z predict, and then Z residual, then histogram normal probability plot. Then you need to check, click continue, then click OK. So here is the output. Here you can see descriptive correlations. Now the only new things I want to show you here is that you can check all the assumptions like before I interpret it. Okay, now let me check the coefficient diagnostic at first, how the model looks like. The coefficient diagnostic, you can see that like if you check the p-value here, only 2 variables are significant, only 3 variables for 0.05. okay, now you can see the other two variables, yeah, here it is very close to, no, this is 0.6. So these 2 variables are not significant, and you can see the p-value is greater than 0.05. okay, so you can select the rest of the variables and interpret it for the rest of the variables as those variables are significant. And before that, as I said, you need to check the Darwin-Watson. It is close to 2. You can also check the graph for like normality, for heteroscedasticity. Okay, so heteroscedasticity, it looks like that there is a particular pattern. Okay, so you can ignore that a little bit, but if you want to do a feed a faceable model, you need to avoid this model. Okay, avoid this regression model. And also you can see what I didn't show in the last model is that how to check multicollinearity, because multicollinearity is actually the relationship between the independent variables. Okay, like as you can see here, there is a term VIF. You can interpret the multicollinearity by using VIF. Okay, like here, if the VIF is close to 1, we can say that there is no multicollinearity. That means there is no relationship between the independent variables that we selected. At simple, we select only one, don't forget that. But at multiple, we select more than one. So for the VIF, you can see that if this value is greater than 10, there is a high multicollinearity. And this is like 3, 4, or 5. If especially it's close to 5, then there is a moderate multicollinearity. So all the value here, you can see the 4, 3, 1. So there is a decent amount of multicollinearity. So this is not a feasible option to go with regression model in this, but you can ignore that a little bit depending on your objective. All right. So now another thing you can do, that the variable which you have like high amount of multicollinearity, like there is no variable which have high amount of multicollinearity, which actually having like moderate multicollinearity, as I said, is close to 5. So you can ignore that. You can just exclude those variables while fitting the model. Okay, so that is how you can go with fitting a regression model. And so yeah, that's all from this video. I hope that you understand how to fit a regression model. I have a plan to create another videos to explain the basic terms more and to provide 1 or 2 more examples. But it will create, I will create a little bit later. I don't know what will be the topic of next videos. If you have any problems, inquiries of anything about this video, you can ask me in the comment box, and you can also knock me, and you can also post in our Facebook group. Okay, so as I mentioned, we have a Facebook group named Data Science Era, and I will also upload this video in our website when our website will launch. So yeah, thank you very much.